Now I will present to our audience the most common questions related to the subject of this Spliced Precast Girders construction stage analysis. So let's get started with the frequent answers questions section that is very fast. The first one here is, what if the user has a previous project data and now has a new project? How can we do it with a slightly different cross-section, let's say? So suppose the user wants to reuse the project data in a similar model. In that case, the user starts in a newly copied, we call it working folder. And then on this working folder, he can modify the references, and the cross-section can be a completely different one. We can migrate from here an example on screen from the girder that was being used on the example to a tub, and still use most of the references, most of the segments, most of the schema that has been built up, and just be able to compare completely different models. And this can be done, and it's done here on the modeler section in the segments type. So another similar issue, but in this case would be inside of the same model, like Anna showed, that we can have different cross sections within the same girder, and Bridge can handle a splice section that could be separate from the beam section. So basically what the user can do, he can copy this original cross section and then modify it by adding more elements to define it. So again, in segments, the cross section references can be changed, and the newly created cross section, it can be applied to the sum of the same elements with the original schema and numbering, like I mentioned before. So it doesn't matter if the change is significant, like the slide before, or a small change, like on this slide. What we want to show that we mostly everything is reusable, precisely as it is inside Bridge, and models can be run either in parallel or even inside the same file, as Anna showed us in the very end of her presentation. So here, what if the user needs to create haunches, splices, flanges? The user can also use the same cross-section technique and apply changes based on the references. So this is what we call parametric modeling, is just to use variables, and by setting up formulas, expressions, or tables, and apply this to the elements according to their axis, like a local alignment or another simple references. He can check the input on screen or with plots. And let's say that if we have stationing for a general alignment, this would be used with numbers that are high, but so it can make a local alignment or a local stationing, and then use this point-wise references related to this local, and then get smaller numbers involved in the definitions, and that could be easier, but it's still references to the general model. So here is more specific question on how exactly is to create a composite beam cross-section. And you can see here that we have the composite part is made of a summation of two parts, and composite are types of parts that can be selected on screen. And this image shows an example of a simple T-beam with an I-girder. The I-girder is here highlighted in red. This is the selected finite element points assigned to this part one, and they define the girder. So if we move on, then we have more elements that are now highlighted. These are the slab, and these elements will be used with different properties, like they will create a completely different area. They have a different nodal eccentricity, and of course they have a different center of gravity. And then, okay, the deck slab over the girder is then assigned as part two, composite only of those elements that were initially black and they are now active and highlighted as red. This will be then also used to be considered as a wet load over the girders for starting, while for the end we'll have the complete composite, and this is what we call the full final composite beam, that is called the part 3 here. And this is then created by putting part 1 and part 2 as acting together. The user can also create multiple composite parts in the cross sections for partial composite. For an U-girder example here, we can see that the partial composite 5 is created by part 1 and 4, as noted in the top. And then later, the full composite part 8 is the same part 1 and 4, but with the addition of part 6 and 7. Then one important thing to notice is that only one composite can be active at each moment in time. And much more useful information about composite modeling and bridge can be found at the links that we provided here in this presentation. Let's explain a little bit more about how users create multiple erection phases for a more complex construction stage. If there is more than a just straightforward phase with deconstruction, like I showed before, 1, 2, and 3 parts, the user can still handle them in the same cross-section. We start with only part 1 as the tub girders shown here in the image 1. Then we add only, let's say in this case, a top precast slab as shown in 2 to get then what is shown as a partial composite that is activated here in the image number as 3. So when we add then the part 4, which would be the tops in situ top slab, and then we can get to the full composite as shown here in 5. This is then be the final element, and then we need to deactivate the elements that were partial before. So the element part 3 has to be deactivated so that we can have the element here in 5. So what is a composite and how we understand it is that to activate a composite action is to integrally bind the materials to work together without slipping between the cross-section different parts. And this connection between parts is created with the necessary studs. These are usually steel connectors. Only then, when we have these steel connectors, the elements will be able to work together as real composites with a more effective cross-section, with more strength and stiffness. So it is not necessarily different materials. It can be different properties like concrete classes or just the age of those concrete elements, like when using a precast girder and later an in situ slab. And this is what allows us to have the strain distribution as shown here. That, for example, at the beginning, we have only the element, the girder, as the first self weight, and the second diagram we have this as the wet concrete on the top, and then any additional load that is loading the full composite, then it is the third image here, but they result together as this final non-linear distribution. So this is what we call the final strain distribution in a composite cross-section, and this is what we get at the end. So how we manage this, to explain a little bit about this redistribution, let's initially focus on the load distribution that should account for the material differences. At the top image, we have the strain distribution in a cross-section part, where the equivalent strain distribution and section forces in the composite cross-section must be joined. So we join individual parts to be converted into a full cross-section analysis. And on the other hand, at the bottom, we have the final resulting non-linear strain distribution in a composite cross-section that should be split into section forces for the top slab. Therefore, to make a conversion of accumulated section forces into an equivalent for each individual components, we split the forces. So the user must do this way because it's the only possibility that allows us to design the individual elements necessary for the full composite. Okay, so this is then how to perform the erection analysis. Just a detail of what was shown by Anna, that we have to include the activation for each stage, and we can have all those details that were shown, and how we create then these stages is on the construction stages activation. So this is where we put specific elements, specific parts are being on and off. Another thing that was mentioned is the temporary support. That is a common issue. And I have shown previous that we can use spring elements to simulate the erection process in the construction stages. if there is a precast girder, if there are temporary supports, shores, something, and that we can use the same model that's it's initially an isolated beam, isostatic, and it will be at the end fully monolithic. Yeah. And then just to make clear that one question that sometimes arises, that do we remove support, clarify that they are not really removed, but the elements are just deactivated. Also the springs are deactivated. And then the elements are reloaded into the structure, so that what happens is that we reapply the loads that are deactivated back to the structure. And one thing that I also mentioned that it's important is to check the tendon positions. And just to mention, we also quite common challenge is the time effects. So creep and shrinkage as well as steel relaxation must be taken care, and this is done when we activate. We can give age, a specific age to the elements, and this is one of the greatest properties that we have inside Iron Bridge, that the time effects are very well accounted for. To conclude, the one common questions that we have to troubleshoot sometimes, it's related to adding details and also to the grillage analysis, so that we have to take care that we have elements that if we create parts separated on the cross section, they are not related to the same point, then we are creating a grillage. And once we create a grid, we create a sequence of nodes, and this will be then parallel nodes, and this will be what creates the grillage. What we need here sometimes is that connection between elements, transversal connection, and we have to take care that we create a good numerical model that allows for load distributions and also the consideration of the orthogonality of elements that is mostly important to get accurate results, especially on skewed elements. So the idea here was to discuss then mostly concrete splice girders modeling. And for our next one, maybe we can have something about steel. That is something that we can also address. And I would like just to finalize to remember that today we only focused on Iron Bridge, but in another opportunity we could address splices in lip bridge concrete, in lip bridge steel, or even in open bridge modeler. So for everyday projects, we remember that as open bridge designer include all of them, the user have not only the freedom to choose, but also the luxury to compare and verify models.
Thanks for watching. If you found this video helpful, please give it a like and share it with others. If you want to see more like it, please consider subscribing to this and Bentley's other channels. Thank you, and see you next time.